This is the second lesson on graphing. In this lesson, we're going to go a little bit deeper to the topic of graphing, and we're going to go beyond polynomial functions and take a look at also rational functions. Those are the functions of the form y equals f of x over g of x, when you have a quotient of two polynomial functions. But before we get to those topics, I'd like to begin with this example on the screen. So you have some information about a function. Given the f prime, the first derivative sign chart, and also the f double prime, second derivative sign chart, the question is asking us to graph the function f of x. And all we really have to do here is to do a rough graph, because we don't know the actual data points. We're never going to know the y coordinates of these x values that are given here. This is x equals 0, this is x equals 4. So we cannot do a perfect graph, but we can still get the skeleton and the rough curvature of this graph, and let's begin. Okay, if you recall on the first derivative, we can get information about increasing or decreasing nature of the graph. So this function is decreasing here, decreasing and increasing afterwards. Now by looking at that, we can do a skeleton. Okay, this graph is going to be basically falling up to the point x equals 4, and it's going to be rising afterwards. Now we don't know how high, like some of you could do something like this, for instance. We don't have y coordinates, but this is the rough shape of the graph from the first derivative information. Based on the second derivative, what do we know? F double prime is positive on the first part. That means it's concave up. Then it is concave down. And then it's concave up again. So up, down, and up again. Now this has to fit in with the previous portion of the graph that we have, the skeleton. So let's see. Up to 0, it should be concave up. So let's see, here's our 0 point. Here's the point 2. And there's our 4. So up to 0, it needs to follow the skeleton, meaning it should be decreasing, but at the same time, it should be concave up. So decreasing and concave up. Okay, a graph like this. From 0 to 2, it should be decreasing based on our dotted line there. It's going downwards, but at the same time, it should be concave down. So there's this subtle change there from instead of up, I changed to down. After that point, everywhere after the point 2, this graph is going to be concave up, but we should still follow the pattern. The pattern was it has to decrease up to 4, increase afterwards, and at the same time being concave up during that interval. So I guess perhaps you already see what this is going to look like, following the dotted lines, but this time with a concave up curve. So there is our rough curve then for y equals f of x. This point here is an inflection point. That point here is an inflection point. Its concavity changed over those points. We also have a minimum, but there is no local maximum for this graph. Okay, the next thing I'd like to do is, before we go and look at the graphs of rational functions, there's one more topic that we need to discuss in this section, and that is finding the absolute maximum and the absolute minimum of a function. You know, we know how to find local max and local min. We take the derivative and set it equal to 0. And, you know, we do a sign chart. If you have a situation like this, you have a maximum, right? If you have a situation like this, at this point, you have a minimum. But this is asking more than a local max and min. In this subtopic, we're looking at an absolute max and min. So that would be like the highest point on a graph, for example. So that would be the absolute maximum. This would be a local maximum, but it is not the absolute max. This is a local min, but not the absolute min. This point right here is the absolute min. So over on the entire graph, the absolute highest and absolute lowest points are referred to as absolute max and min. Now there is a theorem of calculus that says if you have a continuous function over a closed interval, the absolute max and min are going to exist. If, on the other hand, you have an open interval, something like this, from -∞ to infinity, an open interval, not a bounded interval from a to b. if you have a situation like that, there is no guarantee that absolute max and min would exist. Like here, there's an absolute minimum, but is there an absolute maximum? A point that you could put your finger on there and say, this is the absolute highest point on the entire graph. No, because these arrows means it keeps getting larger and larger. So in this situation, there is no absolute maximum. So typically when we ask you to find absolute max or min, we're going to give you a function, a continuous function, and we're going to give you an interval from A to B. Let's say this is A to B. And then we're going to say find the maximums, absolute max and min in that interval. Here's how we do it. First, you will still need to locate the critical points. So set f prime equal to 0 or find f prime is undefined. Second, we're going to evaluate the function at the critical points as well as at the endpoints of the interval. Why do we do that? Because you see, endpoints are candidates to give us absolute max or min points, but sometimes you can have a situation like this. So the absolute maximum point on the graph can also occur at a critical point. So we're going to evaluate the function at the critical points and at the endpoints. These are the suspicious points where you expect to find the absolute max or min. And the highest value you get from that process is your absolute max, and the lowest value you get is your absolute min. Let's take a look at an example. And I will do the second one on this page. F of x equals x cubed minus 12x. The interval is from 0 to 4. The question is, find the absolute max and min for this function. So let's begin. First, we're going to locate the critical points. Set f prime equal to 0 for that. So 3x squared is 12, x squared is 4, x is plus or minus 2. Here's the thing though. Look at this interval. We're trying to find the maximums within this interval. And negative 2 doesn't even lie in that interval, right? So from these critical points, the only one I'm going to select is the positive 2, because negative 2 is not in that interval. It cannot possibly be an absolute max or min. So look what I did here. I took the endpoints of the interval, as well as the critical points that line that given domain in that interval. And I'm going to plug each one into f of x. And then we're going to find the corresponding y coordinate. So let's see what we get. So if I substitute 0 for x, I'm going to get 0. Let me plug in 2. 2 to the third is 8 minus 12 times 2, or 24. So that'll give me negative 16. And plug in a 4, we'll have 64 minus 48. And that should be 16. So now look at your second column values. The absolute largest value you got there, 16. This is going to give you 4 comma 16 is your absolute max. And the absolute lowest number you get on the second column, that is going to give you, so 2 comma negative 16 is your absolute minimum for this function. Okay, the next and the major topic of today's lesson is graphing rational functions. And here's how we're going to do it. First step, we will find all the asymptotes for the rational function. You might have horizontal asymptotes or vertical asymptotes or slant asymptotes. How do we find them? To find the horizontal asymptotes, we need to find the limit of the function as x goes to plus or minus infinity. This is where those limits that we've learned, those shortcut rules in the topic of limits way back at the beginning of the semester, they'll be very handy. Why are we finding a limit? Because ultimately, a horizontal asymptote is a line that a graph approaches towards as x goes towards infinity or towards negative infinity. So basically, if you take a limit, that will tell you what is happening in these extreme regions. And that will give you information about asymptotes, where that function is approaching. Vertical asymptotes occur when denominator is equal to 0. If there are any common factors with the top, please remove those first because those are your removable discontinuities. But if there are no cancellations, then just take the bottom, set equal to 0. Those will give you the vertical asymptotes. To get the slant asymptotes, and these only exist when the degree of the top is exactly 1 higher than the degree of the bottom. To get slant asymptotes, we're going to do a division, and y equals the quotient will be the slant asymptote. And a slant asymptote basically is a slanted line. So let's say maybe this is a graph. So it's possible your rational function looks like this or like that. So notice that the graph is approaching to that slanted line either as you go towards infinity or as you go towards negative infinity. And why is it a slanted line? Well, if the degree of the top is exactly 1 larger than the bottom, say you have something like this. If you divide a third degree with a second degree, you will end up with a first degree, right? So this will be something, a function of x, let's say something like ax plus b, and you could have some remainder terms, but that ax plus b is going to give you the slant asymptote. And the remainder terms basically end up going towards 0. That's why we don't consider that as we're finding our slant asymptotes. Okay, let's go ahead and take a look at some examples. By the way, in this section, we're going to take an easier approach. We're not going to find the first and second derivatives of the given function, and we're not necessarily going to create those sign charts. From past experience, when I ask students to do that, it gets so messy. No one gets to the second derivative correctly, and that of course impacts the sign chart. And basically I find out that I'm not really checking calculus here, I'm checking students' algebra, and if they fail the algebra, they're not able to show me the calculus portion. And because graphing calculators are so widely used, I consider graphing as a topic that is receiving decreased attention in this day and age. So we're going to take a shortcut here and just understand the general ideas about graphing. And I will still be able to show you some ideas with calculus as we do some of the graphing of these functions. Like I'm going to give you a sign chart for f prime, a sign chart for f double prime, and from there I'm going to ask you to graph. And in those types of questions, you still have to use the ideas of derivatives. Okay, but typically we're going to get the asymptotes, we might plot a few extra points, and then we're going to check the answer on the calculator and create some kind of a graph. So this is, again, a decreased attention section. We're covering it lightly just to get an overall understanding of what's happening with rational functions. So this is our series of steps. We're going to find the asymptotes. Typically we'll also find the intercepts. We'll pick test values from the regions determined by the asymptotes just to plot a few points. Sometimes the intercepts are going to be all you need. Again, I'm keeping this as an option. It's not mandatory to do the sign charts for f prime and f double prime. And then we're going to draw a rough curve, keeping in mind your asymptote information and your the points that you have obtained. So here's the example. Let's graph f of x equals 3x squared plus 1 over x squared minus 4. So let's begin with the asymptotes. Okay, first the horizontal asymptote. Take a limit of the function as x goes to plus or minus infinity. What do we get? What we have here is something where the degree of the top equals to the degree of the bottom, right? And we've learned some shortcut rules from earlier in this semester that if the degrees are equal, you take the leading coefficients. So it's going to be 3 over 1 or 3. This tells me that y equals to 3 will be your horizontal asymptote. And just as a refresher, if the degree of the top is smaller than the bottom, something like this, the limit is 0, right? And if the degree of the top is higher than the bottom, then it will go to plus or minus infinity, which means no horizontal asymptote. And if the degree of the top is 1 higher than the bottom, there will be a slant asymptote. Okay, so we know for this example there is a horizontal asymptote. There is no slant. And how about the vertical? set the bottom equal to 0. So x equals x squared is 4, x equals plus or minus 2. Two vertical asymptotes. So already we have an idea about what this graph is going to look like. The vertical asymptotes at plus or minus 2. Horizontal asymptote at 3. Okay, let me also find the intercepts. What is going to be the y-intercept? Set x equal to 0 for that in the original function, and you will get y equals f of 0. We get negative 1/4, plugging 0 for x in this equation. And let's also find the x-intercept. This time set y, or the entire equation, equal to 0. You can multiply both sides by x squared minus 4. That will disappear on the right hand side. So this is as if you're setting the top equal to 0. And in this case, it turns out that x squared is negative 1/3 if you solve this equation. And basically there is no solution, so there will be no x-intercept for this function. And like I said, to complete the graph, at this point you can also check with your graphing calculators. And typically we also plot a point from each of the intervals determined. So for instance, in this interval, let me select x equals to negative 3. In between the vertical asymptotes, let me select negative 1 and positive 1. I'm going to pick 2. And in the outside interval beyond 2, let me pick the point 3. Plug those into the original function. And let's see what we get. Of course, we also have our x-intercept, rather the y-intercept, which was negative 1/4. So we know that point is going to be on this graph. So plugging x equals 1, I'm going to start with the easiest one. On the top I have 3 plus 1 or 4. On the bottom 1 minus 4 or negative 3. That's negative 4/3. By the way, plugging negative 1, I'm going to get the same exact answer because x is being squared. You lose a negative anyway, so it's going to be the same exact answer. Negative 4/3. So already I know. So that's like negative 1.33. And looking at the asymptotes, these are the vertical asymptotes, and the points, I can get a rough idea about what this graph is going to look like. It has to approach the asymptotes. It has to go through those 2 points, so we have something. Now let me give you a moment to go ahead and plug in x equals to 3 and negative 3 and see what you're getting for the y values. So plugging 3 in, 3 times 3 is 9, 9 times 3 is 27, plus 1 we get 28, divided by 3 squared is 9, minus 4 is 5, so we're getting 28/5. And I believe this turns out to be 5.6. It's 5 3/5, right? And the other one, negative 3, will give you the same answer, 5.6. So roughly speaking, at negative 3, we have a point up here, and positive 3, we have a symmetrical point over here. So given the asymptotes, we can now finish the function. It has to approach the horizontal asymptote and the vertical. and it has to go through that point. So we know it's going to be in this quadrant. Like another possibility was like it could have been on this quadrant, but because the point we plot is on the other one, we go with the upper quadrant there. By the way, a graph can cross its horizontal asymptote. Like you could say that this was a horizontal asymptote. You could have a graph that goes like this, but it will never cross its vertical asymptote. So like I said, we did a rough job here, and you can verify this on the graphing calculator, and that is pretty much all I'm asking you to do when you graph rational functions. All right, let's do another example. Okay, this is the one we're going to do next. Let's begin with the asymptotes. The vertical asymptote will be x equals to 3. Horizontal asymptote is none because the degree of the top is 1 higher than the bottom, but there will be a slant asymptote. So let's do the long division. So when you do long division, look at the leading term of the divisor and leading term of the dividend. So x goes into 2x squared how many times? The answer is 2x times. And whatever we write there, we need to multiply it by the divisor. So 2x times x is 2x squared. And 2x times negative 3 is negative 6x. Now to subtract, I just change the signs. And I will add. So the 2x squares cancel. Negative 9x plus 6x is negative 3x. And we bring down to 4. Now we ask the same question. X goes into negative 3x how many times? And the answer is negative 3 times. So we're going to put up there a negative 3 or minus 3 and multiply that with everything you see over here. So negative 3 times x is negative 3x. Negative 3 times negative 3 is 9. Now change the signs and add. So 4 minus 9 is negative 5. So what we're saying is this original function can be written as 2x minus 3 minus 5 over x minus 3. And as x goes towards infinity, this quantity will be going towards 0. Do you see why? Because the bottom is getting larger, the top is fixed, right? So as x goes to infinity, your function will resemble this line, and that line is your slant asymptote. Y equals 2x minus 3. And what about the intercepts? Y-intercept, set x equal to 0, you get 4. And x-intercept, set function equal to 0, again, you can multiply both sides by x minus 3. That's going to disappear from both sides because 0 times anything is 0. So you'll be left with this. Let's see if this factors. How about negative 4 and negative 1? The product of negative 4 and negative 1 is 4. Inner plus outer will give you the negative 9x. So this works. Setting each one equal to 0, we're going to get x equals 1/2 and x equals 4. These are your x-intercepts. Now let's put the pieces together. First, the asymptotes. The vertical asymptote is at x equals to 3. The slant asymptote is y equals 2x minus 3. So that in itself has a y-intercept of negative 3. And if I plug in let's say x equals 1. Actually, let me find the x-intercept of that. So set equal to 0. You get x equals 3/2, or 1.5. So this is going to be your slant asymptote. And then we know the graph should cross the y-axis. This is the y-intercept. When x is 0, y is 4. And we know it should cross the x-axis at 0.5 and 4. So we're supposed to graph the x-intercepts, but when I look at it, it makes no sense because it looks like if I plot the x-intercepts, it's not going to be easy to graph also through the y-intercept and be approaching the asymptote. So I'm going to go back and try to debug my work. And when I do that, you probably knew this all along and you were watching anyway. The y-intercept, when x is 0, I should also plug in 0 for x, right? So sorry about that. That should be -4/3 because when you plug in 0 for the top and for the bottom, you're going to have 4 at the top and -3 at the bottom. So that should be really -4/3. But this is good. You know, we make mistakes and it's important to catch your mistakes along the way. If you check the consistency of your work, like in this case, the points, you know, I'm trying to plot them. It just, they didn't make sense plugging all of them together. Because if I was to plot with the current y-intercept, the 1/2 and the 4, you know, I would have to kind of make something like this, and I know this graph couldn't be like that, so that prompted me to go back and find my mistake. And I encourage you to do things like that. Check your work so you can catch your own mistakes as you go along. Okay? So, -4/3, -1.33, that's where my intercept should be. My y-intercept, x-intercept is 1/2, and at 4. Remember, the graph is approaching its asymptotes, so this is going to be one part. Excuse me, went too far there. One part of the graph, and the other part is going to be approaching the asymptotes and going through that line. That's what we have. The only other possible option, typically your graph could also look like this, over here and over there. But given the x-intercepts, I knew the graph couldn't be there. It had to be on the other two regions. Of course, at this point, you're welcome to go and check your work. Enter everything into the graphing calculator. And you can verify this graph using your graphing calculator as well. I would suggest that you also try another example. Let me check something here. Yeah, also try this one as another example. And please pause the video at this point and then come back to check the solution.